Welcome back. In this lecture video, we're going to look at how to determine the sample size for estimating an overall population mean with a specified margin of error. Now, in the context of stratified random sampling, there are several population characteristics that we need to take into consideration that impact the sample size required in order to come up with an estimator with a given margin of error. In particular, the individual strata sizes, the strata variances, and if we take cost into account, then also the cost associated with sampling the various strata. So the first formula that we look at will give us a way to calculate the overall sample size required in order to estimate the population mean with a given margin of error. So let's take a look at this. A stratified random sample is to be selected from a finite population of size cap n, with stratum sizes cap n1, cap n2, and so forth up to cap n sub l, and stratum variances denoted by sigma 1 squared, sigma 2 squared, and so forth up to sigma sub l squared. Now the goal is to estimate the overall mean of the population, mu, with a margin of error of no more than e. An overall sample size, little n, that will accomplish this is given by this formula here we have on slide 27. And if we look at this formula, we see that most of the terms in this formula are known to us at this point. The strata sizes, the n sub j's, the strata variances, sigma j squared, and so forth. But there is one piece of notation here that we haven't seen yet, and that is these omegas. So omega j is defined to be n sub j over n, little n sub j over little n, and this is the proportion of the overall sample size that is allocated to the jth stratum. All right, and so with that in mind, for a given set of allocation proportions, or we'll call them allocation ratios, and then given values of the strata sizes and the strata variances, we can, and then also given a desired margin of error, we can come up with the sample size, the overall sample size that will give us an estimator of the population mean that has a margin of error no more than cap e. At least that's the goal. So let's look at an example. Continuing the advertising example, suppose that a prior survey suggests that the variance of stratum 1, sigma 1 squared, is approximately 25 hours squared. The variance of stratum 2, sigma 2 squared, is approximately 225 hours squared. And that the variance of stratum 3, sigma 3 squared, is approximately 100 hours squared. The desired margin of error for the estimator of the population mean is 2 hours. So we want ideally we want the sample size that we obtain to provide for us an estimator of the population mean. So the estimator being mu hat, we want the variance of, we want the margin of error associated with mu hat to be no more than 2 hours. For each set of allocation ratios given below, find the overall sample size that will provide this desired margin of error as well as the individual stratum sample sizes. So we have 3 sets of allocation ratios here. The first essentially gets 1/3 of the overall sample from each of the 3 strata. In the second set of allocation ratios, the proportions, the allocation ratios, are equal to the proportional size of the strata across the entire population. In other words, stratum 1 contained the proportion of the overall population size that is contained in stratum 1 is equal to 155 over 310. The proportion of the overall population size that is contained in stratum 2 is 62 over 310, and so forth. And so essentially what we're doing here is selecting samples from the 3 strata that are proportional to the strata sizes. Now the third set of allocation ratios, instead of looking at the strata sizes, looks at the variances associated with the 3 strata. And if we were to add up the variances of the three strata, which by itself is kind of a meaningless thing to do, but for the sake of the example, let's just do this. Then what the third set of allocation ratios do is allocate or select from each of the three strata a sample size that is proportional to the total of the variances across the population. All right, so let's take a look at this. Let's look at this first set of allocation ratios. And so again, with these allocation ratios, we are getting 1/3 of our sample from each of the three strata comprising the population. Using these allocation ratios, the sample size formula returns an overall sample size of little n equal to 56.7, which along with the allocation ratios gives stratum sample sizes of 18.9 from each of the three strata. Now, these are obviously not legitimate sample sizes, since sample sizes must be whole numbers. We'll talk about that in a few minutes. But for now, what I want to do is to consider these calculated sample size as they are for the overall and the stratum sample sizes. And what I want to do is go back now and use these calculated values for sample sizes and determine what the variance of mu hat would be with these sample sizes. All right, and so if we do that, then the actual variance of mu hat would be 1.0114. And then once we have the variance of mu hat, we can take the square root of that to get the standard deviation of the sampling distribution of mu hat, and then multiply that by 2, and then that value would be the actual approximate 95% margin of error associated with mu hat. Now I say actual rather than estimated because we don't have a sample yet, right? And we are assuming here that we know the population strata variances. All right, and so with that information, then the margin of error associated with mu hat would be 2.0114. Now, recall that the goal was to determine the overall sample size that would, in conjunction with the specified allocation ratios, result in a margin of error of no more than 2 hours. And yet the margin of error is slightly more than that, at 2.0114 hours. And so the question is, why is this? I mean, did we commit a calculational error? Well, no, we did the calculations correctly. The reason that the margin of error that we've obtained using this sample size formula, the reason that that margin of error is not less than or equal to the 2 hours that we wanted it to be, is that the sample size formula that we used, all right, so let me go back to that slide real quick. This sample size formula here is based on a simplification of the formula for the variance of mu hat. All right, so in deriving that sample size formula, what we had to do was to slightly simplify, use a simplified version of or approximation to that variance formula to derive that sample size formula. And so that is the reason that the margin of error is not exactly equal to 2 hours. Now, because of this, in some cases, the resulting margin of error of mu hat may not be less than or equal to the desired margin of error. And so we'll have to think about how to deal with that. Now, the other problem, as we've seen, is that the formula does not necessarily return whole numbers for the sample sizes, which obviously is required for an actual sample size. Now, these problems are easily resolved, though. The second problem, involving fractional sample sizes, is resolved by either rounding the calculated sample sizes to the nearest integer or moving non-integral values up to the next integer sample size like we did in the context of simple random sampling. The first problem can be resolved by using the calculated sample sizes as starting values and then incrementally adjusting, increasing them until the criterion involving the margin of error is satisfied. Or for this first problem here, maybe we just don't do anything, right? Maybe we say that if we get close to that margin of error, then that's really all that's necessary. And that's probably, in practice what we would do. Okay, let's look and see how we can adjust these numbers to resolve both of these issues. All right, and so here I've got a table, and I've got, in the first column here, I've got the source of the sample size numbers that I have in the various columns. And so in this first row, these are the sample sizes that we've calculated using the sample size formula. And so again, the sample size formula gives us an overall sample size of 56.7 observations, and then multiplying that against these allocation ratios, we get 18.9 observations from each of my three strata. And as we indicated, if we then go and use the formula for the variance of mu hat, which is in the notes, go back and look at it, if we apply these sample sizes, if we plug these sample sizes into that formula, we see that the variance of mu hat would be 1.0114, and then the associated margin of error of mu hat would be 2.0114. Now again, obviously, we have to get integers here for sample sizes. We can't use fractional values. So the first approach that we'll look at here is what if we just round, and when I talk about what I'm doing here, I'm talking about doing this operation to the individual strata sizes. And so what if we round these values to the nearest integer? So in this case, these would all round up to 19 observations. And if we do that, then we would get 57 total observations. Now that would preserve, notice that would indeed preserve the allocation ratios that we've got specified here. And if we do this, we see that and then plug these sample sizes, the stratum sample sizes, into the formula for the variance of mu hat, we would get a variance of mu hat equal to 1.00541. We take the square root of that and then multiply the square root by 2 to get the margin of error, and that would be 2.00541. So it's closer to 2, but it's not less than or equal to 2. All right? So this resolved the non-integer problem, but we still haven't resolved getting this thing less than or equal to 2. Now, maybe this is close enough, all right? In practice, that's probably what we would do. Well, let's look and see what can we do to adjust these stratum sample sizes to get at or below 2. And so one approach would be to increase all three, to increment by 1 all three of these stratum sample sizes. And so increase each of these up to 20. And if we do that, then the overall sample size would increase to 60. And notice again that the allocation ratios have been preserved. Okay, and so if we do that and then plug these sample sizes into the formula for the variance of mu hat, we see that we get a variance of 0.94085. The corresponding value for the margin of error of mu hat would then be 1.93994. And so we do see that that is less than or equal to 2, the desired margin of error, which was 2. Now, another approach, instead of incrementing all three of these stratum sample sizes, we could try incrementing just one of them. And so, for example, if we increment N1 by 1 and leave N2 and N3 the same, so we have 20 observations from stratum 1 and 19 observations from each of strata 2 and 3, then we have an overall sample size of 58. The variance of mu hat would then be 0.98886, and the margin of error of mu hat would be 1.98883. And so you see we do have a margin of error that is less than or equal to 2. And notice that this sample size is less than what it was on the last row of the previous slide with 60 observations, which also gave us a margin of error of less than 2. Now, instead of incrementing N1, we could increment N2 and leave N1 and N2 alone, leave those both at 19. And if we do that, then we get a variance for mu hat of 0.98134, and a margin of error of mu hat equal to 1.98125, which again is less than or equal to 2. And then finally, we could increment N3 alone, leave N1 and N2 at 19. Again, we get a total sample size of 58, and then with those 3 sample sizes, the variance of mu hat would be 0.98147, and the margin of error of mu hat would be 1.98139. Now notice that depending upon which of these stratum sample sizes that we increment, we get slightly different values for the variances of mu hat and the margin of errors of mu hat. And you can see here that, for example, if we, by increasing N2 by 1 and leaving N1 and N3 alone, we actually get an overall smaller value for the margin of error of mu hat, although not much smaller, but it is a little bit smaller than both of the other 2 scenarios. So that is one way that we can deal with this issue that results from the fact that the sample size formula is derived based on a simplified version of an approximation to the actual formula for the variance of mu hat. And so this formula, if we go back up here, this formula gets us in the ballpark, and it will tend to get us very close. All right, but we do need to understand, and I don't want you to be confused. If you calculate a sample size, calculate the corresponding stratum sample sizes, and then end up, if we calculate that margin of error, if we get something that's not quite as small as what we've desired, there's a reason for that. We know what that reason is now, and we can deal with it. Okay, now let's look at the second scenario, where the allocation ratios are equal to the proportion of the population size for each of the 3 strata. So omega 1 is equal to 155 over 310, which is 0.5. Omega 2 is 62 over 310, which is 0.2. And omega 3 is 93 over 310, which is 0.3. So with this set of allocation ratios, whatever our sample size ends up being, this says we're going to get half of our sample from stratum 1, 20% of our sample from stratum 2, and 30% from stratum 3. Now, using these allocation ratios, the sample size formula returns an overall sample size of 68.2, and along with the allocation ratios gives stratum sample sizes of N1 equal to 34.1, N2 equal to 13.6, and N3 equal to 20.5. Now these values with the resulting variance and margin of error are given in the table on the next slide. The table also shows the results of dealing with the non-integral sample sizes in a couple different ways. And so again, the calculated value for the overall sample size is 68.2, and then multiplying that against the 3 allocation ratios, that would result in stratum sample sizes of 34.1, 13.6, and 20.5. Now, with that set of stratum sample sizes, plugging those values into the formula for the variance of mu hat, we get a variance of 1.0131. Taking the square root of that, multiplying by 2, we get 2.0130 for the margin of error of mu hat. And again, that is not less than or equal to 2. All right, but again, we realize that that sample size is based on an approximation, so it's really an approximate sample size that gets us close to the actual sample size that would give us that margin of error. And so let's first look at rounding. Let's round each of these sample sizes in the first row to the nearest integer. So 34.1 rounds to 34, 13.6 rounds to 14, 20.5 rounds to 21. If we do that, then we get an overall sample size of 69. Now notice that that is not 68.2 rounded, right? But again, what we're rounding here is not the overall sample size, but we're rounding the stratum sample sizes. So with these 3 stratum sample sizes, If we plug those into the formula for the variance of mu hat, we get a variance of equal to 0.98569. We take the square root of that, multiply the square root by 2, we get 1.98564. So that does, using that approach in this particular example, does get us to a margin of error that's less than or equal to 2 hours. Now, we could also use the approach where we use the next larger integer for each of these 3 sample sizes. Any sample size having a decimal portion, we could take up to the next larger integer. So if we do that, we would go up to 35. From 13.6, we would obviously go up to 14. And from 20.5, we would go up to 21. So if we do that, then we have an overall sample size of 70 observations. And by the way, with that, that does preserve the allocation ratios. All right, so if we use those 3 sample sizes, plug those into the formula for the variance of mu hat, then we get a variance of mu hat equal to 0.9804, so a little bit less than this one, which makes sense because we've got a little bit larger sample size. And taking the square root of that variance and multiplying by 2, we get the margin of error for mu hat being equal to 1.9803. And so again, we see that we get a sample size, an overall sample size, and the individual stratum sample sizes, which result in the margin of error of mu hat being no more than the desired 2 hours. Now let's look at this last set of allocation ratios. Omega 1 equal to 25 over 350, omega 2 equal to 225 over 350, and omega 3 equal to 100 over 350. Using these allocation ratios, the sample size formula returns an overall sample size of 103.7 observations, which, along with the allocation ratios, gives stratum sample sizes of 7.4 observations from stratum 1, 66.7 observations from stratum 2, and 29.6 observations from stratum 3. Now, before we bother looking at options for dealing with the non-integral sample sizes, note the following. The calculated sample size for stratum 2 is 66.7 observations, but stratum 2 only has 62 members in the population. And so in other words, the calculated stratum sample size is greater than the number of members in stratum 2. And so it follows that this particular set of allocation ratios is not feasible for this particular population. So we're really not even going to consider this any further. Now, what I want to do is to go back and look at the sample sizes for the first 2 allocation ratios. So let me go back here. Here is the first table for these allocation ratios, which each are 1/3. And notice that the sample sizes here, depending upon whether we round the individual sample sizes or bump up each one in order to get down below 2, or if we bump one sample size individually, look at the 3 scenarios there, the sample sizes range from 57 to 58 to 60. So that's the range of sample sizes that we're looking at with this set of allocation ratios. On the other hand, notice that with the second set of allocation ratios, the required sample sizes are larger. 69 and 70 observations is what we came up with. And so what this shows us here is that the sample size required in order to have an estimator for the population mean with a margin of error of no more than a given value is very much going to depend on the allocation ratios that we're using. All right, so we need to think about that very carefully and come up with, if we can do it, we want to come up with allocation ratios that are in a sense optimal. That will result in the smallest sample size possible for attaining a margin of error of mu hat that we can come up with. And so that is going to be something that we'll look at in a second. Now, example 4 in the notes says that for the previous example, calculate the variance of the sampling distribution of mu hat, the estimator of the overall population mean under each scenario considered. Well, we already did that, right? We did that in this next to last column in each of these tables. And so what I would recommend that you do is go through and do these calculations, all right, and make sure that you can get all the values in these tables, the sample sizes, the variances, the actual margin of error, and so forth. Okay, so now let's move on. And on this slide, we look at allocation of sample size across strata to minimize the variance of the estimator of a mean. Now, for a given overall sample size, the variance of the sampling distribution of the estimator of the overall population mean depends on the following characteristics: the strata sizes, in other words, the cap n sub j's, the strata variances, and the sizes of the samples selected from the various strata. Now, this means that the margin of error associated with that estimator will also depend on those population and sample characteristics. For a given population, the strata sizes and the strata variances are obviously fixed. The sizes of the samples selected from the various strata, however, are under the control of the experimenter and can be varied. For a given population and for a given overall sample size, the variance of the sampling distribution of the estimator of the overall population mean will vary depending on the allocation of the overall sample size across the various population strata. In general, it's desirable to have estimators with as small a variance as possible. For a given overall sample size, little n, the allocation ratios that minimize the variance of the sampling distribution of the estimator of the population mean are given by the formula here on slide 31. And so this is showing us how to come up with allocation ratios that are optimal in the sense that they provide an estimator that has the minimum variance possible. All right, so let's look at the next example. Continuing with this advertising example, find the allocation ratios that minimize the variance of the sampling distribution of the overall population mean estimator mu hat. As before, assume that sigma 1 squared is 25, sigma 2 squared is 225, and sigma 3 squared is 100. Now, once the variance minimizing allocation ratios have been determined, use those ratios along with the previous result, that previous overall sample size formula, to find the overall sample size that will ensure that the margin of error associated with the estimator is no more than 2 hours. Find the individual strata sample sizes as well. Finally, find the variance of the sampling distribution of mu hat for this particular allocation. Okay, so we want to find the allocation ratios, and this is the formula that we'll use to do that. Now, notice that the denominator is the sum of the values in the numerator for the 3 strata. So what I'm going to do is just calculate n sub j times sigma sub j for each of the 3 strata. Now, notice that the formula calls for sigma sub j, not sigma squared sub j. So these are the strata standard deviations. So we need to be careful that we take that into consideration here. And so these are the products, the strata sizes times the strata standard deviations. The sum of those values is 2635, and so the allocation ratios are given by each of these values over 2635, and so that's how we come up with these values here. Now, we can do a quick quality control check. These need to add up to 1, and if we add them up, then we see that we do get 1, and so we can be fairly sure that we've done these calculations correctly. So for a given overall sample size, whatever it happens to be, little n, these allocation ratios will result in mu hat, the estimator of the overall population mean, having the smallest possible variance. Okay? And so these are the allocation ratios that would provide that minimum variance estimator of mu. Now, using the allocation ratios determined above, find the overall sample size that will result in mu hat having a margin of error of no more than 2 hours. Okay, so now we need to go back and use the first formula that we looked at in this lecture video, that formula for calculating the overall sample size. And you can pause the video, and I'm going to calculate the various pieces of that formula on these handwritten notes. And so you can pause the lecture video, take a look at what I'm calculating. All right, do the calculation yourself and make sure that you come up with the same value I got. Okay, now the denominator does not depend on the allocation ratios, so it does not need to be recalculated. Well, I didn't show you the calculation before. I'll let you go ahead and do that. All right, and you will have done that as part of working out that previous example. Okay, now you can see here that in that previous example, when you do that work, it turns out to be, this is again the denominator of the sample size formula. It turns out to be 123,225. And so when we use these optimal allocation ratios in this formula, we get an overall sample size of 56.3. And again, that's we need to have an integer, and so we would go up to the next larger integer for 57. All right, and so note that because the allocation ratios being used result in mu hat having the minimum possible variance, this sample size is the smallest possible sample size over all population allocations that will result in mu hat having a margin of error of no more than 2 hours. And again, we're realizing here that this is an approximation. All right, we may need to tweak it once we calculate the actual margin of error. Okay, so if we take that 57, that rounded value, not rounded, but bumped up sample size, and apply these allocation ratios, we get stratum sample sizes of 16.8 for stratum 1, 20.1 from strata 2 and 3. And then we might, for example, round these to the closest integer, so we could use 17 observations from stratum 1, 20 observations from each of strata 2 and 3. Okay, now let's use those stratum sample sizes to calculate the true variance of mu hat using these sample sizes and the formula for the variance of mu hat from the previous work in the notes. And so when we do that, we find that the variance of mu hat is equal to 0.9964. Okay, and then taking the square root of that value and multiplying it by 2, we get a margin of error associated with mu hat of 1.9963. And that is, in fact, less than or equal to the desired value of 2 hours. Now, note again that little n equal to 57 is the smallest possible sample size for which the margin of error of mu hat will be no more than 2 hours. For any smaller sample size, it will be the case that the margin of error of mu hat is greater than 2 hours. Now we can put these results together in a combined type of formula. Given a desired margin of error, cap E, the minimum overall sample size and allocation proportions needed to minimize the variance of the estimator of the population mean can be determined. The overall sample size required is given by this expression here. All right. And notice that this formula for n does not involve the allocation ratios. Right? It involves only the strata sizes, the strata standard deviations, or the strata variances, and the overall population size, and which is the sum of the strata sample sizes, and then the desired margin of error. Now, once we have this overall sample size, little n, this overall sample size is then allocated across the strata according to the allocation given on the previous few slides. And so we could then, once we get this overall sample size, we can then go back and calculate the optimal allocation ratios, and then use this overall sample size in conjunction with the optimal allocation ratios to get the optimal sample sizes from each stratum. And so let's look at this in the context of this example. So for the advertising example, use the result on the previous slide to find the minimum overall sample size that will ensure that the margin of error is no more than 2 hours. Okay, So we use the formula from that slide. So here again is the formula. All right, and from previous work we know that the sum of the products of the stratum sizes and the stratum standard deviations is 2635. And we can calculate the denominator using these values that I've got listed here. So you can pause the video and you can do the calculations and make sure that you come up with the same value. And so when we do that, we apply this formula to get the smallest sample size that will give us a margin of error of no more than the desired margin of error, which was 2 hours. And we see that we get the exact same value that we got previously, 56.3, which we could bump up to the next integer of 57. And so this is consistent with the sample size obtained from the previous example. Okay, and so we see that we've got really two directions that we can come at this from. We can use the previous approach where we found the optimal strata sizes and found the overall sample size, or we can use this formula to first get the overall sample size that will give us a margin of error of no more than cap E, and then the previous formula, which gave us the optimal allocation, all right, and then in conjunction with that, come up with the strata sizes. Now we're going to look at an allocation of sample size across strata to minimize the overall cost of sampling. Now suppose that the sampling costs per unit are known for the various strata, and that it is desired to estimate the overall population mean at minimum cost. How should a given overall sample size be allocated across strata in order to accomplish this goal? Now denote the sampling cost per unit for stratum J by C sub J, J going from 1 up to cap L. For a given overall sample size little n, the allocation proportions that minimize the overall cost of the sampling procedure is given by this formula here. So we're again calculating these allocation ratios, but in this case, we're instead of minimizing the variance of mu hat, we're minimizing the cost associated with sampling. Now the overall sample size needed to estimate the population mean at minimum cost with a specified margin of error, cap E, is given by this formula here. So now what we're doing, on the previous slide we found the allocation ratios, but what we can do is also find the overall sample size needed to estimate a population mean with a specified margin of error, and do so at minimum cost. Okay, so again, what we're doing here, we want to estimate mu. All right, that estimate is denoted by mu hat. We want the margin of error associated with mu hat to be no more than cap E, and we want to do this at minimum cost. Now, the overall sample size that will accomplish this is given by this expression here. And then once we have this, then this overall sample size little n is allocated across the various strata according to the allocations given here. So n sub j would be equal to the overall sample size times this allocation rate, what turns out to be an allocation ratio. All right, so example 7. Continuing with the advertising example, suppose that the firm finds that obtaining an observation from a rural household costs more than obtaining a response in town A or B. The increase in cost is due to costs of traveling from one rural household to another. Now the cost per observation in each town is estimated to be $9, while the cost of observation in the rural area is found to be $16. Find the overall sample size little n and the stratum sample sizes n1, n2, and n3 that allow the firm to estimate at minimum cost the average television viewing time such that that estimate has a margin of error of no more than 2 hours. Okay, now this can be done in two ways. The first way is to find the allocation ratios that minimize the overall sampling cost using the formula on our previous slide, and then to use these ratios in the formula for the overall sample size on slide 27, way back, that very first slide that we looked at in this lecture video. Or, option number 2, find the overall sample size first using the formula on slide 36, and then use the formula on slide 35, which is reproduced on the bottom of slide 36 to find the allocation ratio. So either way, you'll get the same result. Now in this example, we'll use the formulas on slides 35 and 36 since we haven't used those yet. Now we need to compute or calculate the following quantities, all right, the various pieces of these formulas. Note that the expression in 3 does not depend on cost, C sub j, and was already calculated in a previous example and was found to be 123,225. Okay, so here is a table showing these kind of organizing the values and organizing the calculation. All right, and here is another table showing the calculation of another component of this formula. Okay, and then this is the expression that we need to find to get the other component, the numerator, for the sample size, and that's the numerator there. And so then we divide that by the 123,225, and we come up with 57.4. Now again, we have a fractional value, and so what we would do is go up to the next larger integer, which is 58 observations. Now, we then come up with the allocation ratios from a few slides back, and so these would be the allocation ratios that would minimize the cost of sampling from this population. And again, just doing a quick quality control check, we see that they add up to 1 as they should, and so we're good to go. Okay, so then applying those allocation ratios to the overall sample size, the 58, we get a sample size of 18.71, which we bump up to 19 observations from stratum 1, 22.45 observations from stratum 2, and I'm going to, in this case, what I'm going to do is round these, so I'm rounding the 18.71 up to 19, rounding the 22.45 down to 22, and I'm rounding the 16.84 to 17. If you'll recall, let me just point out here, you'll recall that when we were looking at sample size calculations in the context of the simple random sampling, we always just went up to the next larger integer. But in this case, it's a little bit more complicated. We have a little bit more flexibility because we've got various strata. And so in this case, what I've done is rounded, and that keeps me in this particular situation at the 58 observations. Now the question is, does doing that actually give me a margin of error of no more than 2 hours? So we need to check that just to make sure. And so we see here that when we calculate the variance of mu hat using these sample sizes, we get a variance of 0.99610. Taking the square root of that and multiplying it by 2, we get a margin of error of 1.9961 hours. And so that is less than or equal to the desired 2 hours. Now, let's take that and look at the total cost of sampling using these sample sizes. All right, so we've verified that the margin of error is no more than what we had specified. All right, and we got that using 19 observations from stratum 1, 22 from stratum 2, and 17 from stratum 3. So now let's calculate the total cost for sampling for this particular experiment or sampling process. And so we see here that multiplying these sample sizes by the cost per unit observation from each of the 3 strata gives us a total of $641. All right. Now, this $641 is the minimum cost possible for obtaining an estimator of mu, again that estimator is mu hat, possessing a margin of error of no more than 2 hours. And this is what I want to point out here. Any sampling allocation costing less than $641 will result in mu hat having a margin of error greater than 2 hours. In addition, any other sampling allocation for which mu hat has a margin of error of 2 hours or less will cost at least $641. Okay, so this is, in terms of cost, this is the optimal sample size and sample allocation ratios that we could possibly use and still have an estimator that has of the population mean that has a margin of error of no more than 2 hours. Okay, so those are the various kinds of things that we need to take into consideration when determining the sample sizes needed for sampling a stratified population. And you can see here that it's very interesting and very useful information because we can optimize what we're doing. We can it's very helpful to be able to know how to come up with a sampling scheme from a stratified population that will result in estimators that have a given margin of error, and also how to do so in a way that is cost effective, in fact, that minimizes the cost of sampling.